Our next presenter really probably needs no introduction, but I will do so anyway. I had the privilege of meeting Jeff Bier probably 25 years ago, maybe 30 years ago, in his primary role as president of BDTI. In that capacity, he's had the wonderful position to analyze and watch the incredible evolution of the technology that we've all been living through. And that put him in a perfect position to realize the right moment when you can actually start talking about the word computer vision. And with that, he was able to use that vision and become found the Embedded Vision Alliance, which has grown from a small group of crazy people who had this vision to 80 companies now that are servicing the industry either as suppliers at the electronics level, the board level, or service level. And it's all part of this incredible revolution that we're experiencing now. Jeff is going to talk to us today about what he sees as the primary trends driving this industry. And so, true words from an expert here on what's exciting and coming forward, I introduce you to Jeff Bier. Thank you.
Thank you very much, Craig. Thanks for that kind introduction. Thank you all for being here at the summit and at my presentation. I was going to title my talk, The 4 Key Trends Driving the Proliferation of Visual Perception, number 3 will amaze you. But the organizers of the conference seem to be a little too straight-laced for that. Big picture. Bottom line, what my takeaway for today, for this presentation, is we're just seeing the tip of the iceberg. We are entering an era of unprecedented activity and acceleration in investment, in innovation, and in deployment of computer vision technology across a very broad range of applications and markets. I'm going to share 3 signals that I think support that thesis. In the lower left, this is a slide from Rudy Berger, from Rudy Berger's presentation yesterday in this room. The big blue arrows are my additions to these slides. But this was, and I realize this is not really legible from the audience, but the idea here is just to emphasize, you see those bars growing exponentially. That's startup investment activity in the US and China in computer vision. The line is the number of companies being funded. The bar is the amount of money being invested. It increases approximately 100x in 6 years through 2017. So that's historical data. Then on the right, this is forecast data from market research firm Tractica for the aggregate computer vision software, hardware, and services business. Their forecast is growth of approximately 25x, 25 times, over the next 9 years, or roughly the next 9 years, from 2016, which is the baseline, to 2025. The third signal comes from our survey, which focuses on developers working in industry, developing systems and applications using computer vision. And mostly we ask them about technical choices and technical challenges that they're facing and making. But we also ask them some of these, like, where do you think, what do you think is going to happen kinds of questions. And one question we ask is, do you think that your organization, typically that's a company, is going to be expanding or decreasing its activity in computer vision over the next year? And we get something close to 1,000 respondents. Again, just people in industry here. This is excluding students and so forth. And you can see that from the most recent administration of this survey, 60% said they expect a large increase in computer vision activity in their organization over the next year. 35% expect a small increase, and roughly 0% expect a decrease, or even staying the same is only 5%. So that's a pretty amazing sort of consensus among the respondents. So what's driving this acceleration? I think it's these 3 things. Computer vision now works well enough in many real-world environments. That wasn't always the case. Often it was very hard to get computer vision to work well enough in real-world situations as opposed to very controlled environments to make it reliable enough that it was commercially viable. That's changing very fast, and I'll explain a little bit some of the things behind that, or identify a little bit some of the things behind that in a minute. Second key is affordability, or maybe looking a little more broadly, cost, power consumption, and size of these now sufficiently accurate vision subsystems is low enough that vision can be deployed almost anywhere. And thirdly, and this is possibly the most important, is that increasingly vision is accessible to non-specialists. People who are not computer vision specialists can increasingly harness computer vision to solve their problems. And this is really important because there's a very limited number of computer vision specialists. So these are the three developments that I think are really driving this explosion in investment, innovation, and deployment of computer vision. And in turn, I think these are undergirded by a number of trends, 4 of which I'm going to focus on here. And the first is deep learning. This is a critical advance in enabling computer vision to work well enough. Right? Previously, companies spent hundreds, even thousands of man-years carefully handcrafting algorithms to solve very specific computer vision problems and honing them over years and years and years. And that's just not scalable. Very, very few applications can justify that kind of expense. With deep learning, it's a whole different ballgame, right? And it becomes mostly a matter of choosing the right existing algorithm and then gathering and curating the right training data to train the algorithm to solve the problem. Deep learning algorithms are, in many cases, approaching or starting to exceed human abilities. This is a chart that shows the ImageNet, the very famous ImageNet image recognition or image classification challenge. You can see the progress over the years, and you can see the red dashed line, that's the approximate accuracy of humans on classifying those images in ImageNet. And so you can see that roughly in 2016, the best deep neural network algorithms, well, the best algorithms that competed in the ImageNet competition exceeded human accuracy, and they're just getting better. In fact, what deep neural networks are capable of these days is pretty amazing. This is work from NVIDIA research. Let me just show you this video, and I'll explain what's happening. On the left-hand side, the user is simply erasing parts of the photograph, and on the right-hand side, a deep neural network is filling in the missing parts of the image. Can we mute the audio, please? Thank you. Just the neural network is filling in the missing parts of the image based on what it thinks should go there. Right? So it's been trained on many, many images, and so it has an idea that based on what else is in the surrounding area of the image, here's what should go in the part that's now missing. So in fact, what we see here is that not only can deep neural networks match human performance of, let's say, a typical person on the street on a task like image recognition, but in fact, they can match, I mean, could you do this? Maybe with some training and skill, right? You could do this. Somebody who's a skilled kind of photo retoucher could do this, but a typical person off the street, you wouldn't expect to be able to do this. And so what this shows, I think, is that deep neural networks, not only can they match or beat a typical person on the street at saying, is this a banana or a lemon or a dog or a cat, but they can actually, at least in some cases, match what a skilled, trained human can do. So how long will it be before this kind of capability is just built into the photo editing app on your mobile phone? Not very long, I think. And this isn't the only example. Neural networks are increasingly going beyond what humans can do, even skilled humans. This is work from University of Illinois, Urbana-Champaign, and Intel. Basically what they did here is they taught a deep neural network to see in the dark by taking dark scenes. And normally, of course, if you want to get a picture of a dark scene, you need a really long exposure. Of course, these scenes don't have zero light, they just have very, very low light. And so normally, if you want to photograph an image of a very, very low light scene, you need a very long exposure. But there are all kinds of problems with very long exposures, including the objects may be moving, the camera may be moving, you may need video, in which case you need short exposures. So they take a long exposure image, and then they take a short exposure image. And then they use those to train the network. Here's the short exposure image is the input to the network. The long exposure input is the desired output. And they get remarkably good results. So what you see on the left is what you get with the short exposure on the camera. It's basically black. And what you see on all the way on the right is what they're able to reconstruct from that after training the network on this superhuman ability to see in the dark. So deep neural networks, I think, are revolutionizing computer vision, making it possible for many more problems to be solved. And we see that, accordingly, they're being adopted very fast in industry. Referring back to this same survey that I mentioned earlier, we see that over 50% of our vision system and application developers in industry responding to our survey are already using deep neural networks for visual perception in their systems and applications, perhaps not exclusively, but using it. And this increased, by the way, from 34% a year prior. So it went from 34 to 50%, or 51% in a matter of a year, or even a little less, actually. Meanwhile, another 34% of the respondents are planning to use deep neural networks. So all told, 85% of respondents are using deep neural networks or planning to. So clearly this is more than just a curiosity. So deep neural networks are a key advance, enabling computer vision to really work in real-world environments. And another recent advance is small, low-cost, low-power 3D cameras and camera modules like those shown here from Microsoft, Intel, and Occipital. Why are 3D cameras important to enabling things to, computer vision to work? Well, it's a 3D world we live in, and having that depth information makes it much easier to know with high confidence what the system is looking at, especially in situations like navigation. You see this color-coded image on the left. That's a visual SLAM output, visual simultaneous localization and mapping, like would be used in a mobile robot to understand its environment. On the right, you see a Apple Face ID kind of image, and I think everyone knows that the latest iPhones have this 3D imaging for the specific purpose of identifying the user for unlocking the phone. And I think it's pretty clear that Apple isn't just toying with this 3D technology. They did careful analysis and decided this was the right way to solve this particular problem. So they put it into production, and now, of course, hundreds of millions of units of mobile phones, not only from Apple, but also from several of its competitors, are being manufactured with 3D imaging of one form or another, and this helps drive the cost, power, and size down further, enabling 3D to go into more and more applications. Also, these 3D imaging technologies, in many cases, use infrared illumination, and that turns out to be super handy, somewhat independent of the 3D capability. For example, if you're creating a driver monitoring system that's monitoring the driver of a car to see, are they getting tired, are they becoming inattentive or distracted, of course that has to work in the dark. And of course you're not going to shine a visible light in the driver's face. So you're going to illuminate the driver's face with infrared, and that's how you're going to get reliable information, whether it's 2D or 3D, but infrared illumination is often part of these 3D modules. About 8 years ago, Microsoft debuted the first generation Microsoft Kinect. Initially, it was very successful as a consumer product, as a peripheral to the Xbox gaming console. Ultimately, it didn't really catch on among gamers. But I think that was really the beginning of a revolution in bringing down the cost and size and power consumption of 3D imaging technology. And as you see in this slide in the lower right, this is from Guillaume Girardin from Yole, from his presentation yesterday. These days, for $20 or maybe $30, you can incorporate a 3D camera module using structured light, stereo, time of flight, or some hybrid technology into a system. And obviously, that's not zero, but that's probably an order of magnitude lower than it was just a few years ago, and therefore, and it's a number that's feasible for many, many applications. Going back to our survey, we see that today about 30% of the developers in our survey are already using 3D perception in their computer vision solutions, with another 21% planning to use it. We looked at this also across industry segments and saw some things that were not surprising. For example, construction applications are the biggest user of 3D technology. This makes perfect sense when you think about the kinds of things you want to do in construction with computer vision. It also makes sense because construction applications presumably are a little less cost sensitive than things like consumer applications. At the other end of the spectrum, consumer applications are lagging the rest of the field in adoption of 3D, and that makes sense because of their cost sensitivity and also often power and size constraints. Even so, though, notice that roughly 50% of the respondents who are working in consumer electronics said that they are using or planning to use, currently using or planning to use 3D in their designs. Okay, so that's a little bit about deep learning and 3D perception. The third area I want to cover is processors. There's a revolution underway in processors for computer vision, especially processors for deep learning-based computer vision. This is a variation of a slide I presented last year that I updated based on some more recent results. And I apologize for all the numbers, the clutter of numbers here, but the basic take-home here is processors themselves for running deep neural network inference are improving over a period of just, let's say, 3 years, like it says on this slide, improving by roughly 100x. You can get a slightly higher number or somewhat lower number depending on exactly which processors you look at and what you compare as the baseline. But let's just say 100x. Why and how is because people are designing lots of processors for the first time that are specifically tuned for these workloads, architected for these workloads. So 100x is a huge improvement, but wait, there's more. Not only are the processors improving, two other things are happening. People are rethinking their algorithms to create versions of deep neural networks, like binary neural networks, that are much more computationally efficient. And we see at least another order of magnitude improvement, independent of the processor improvements, in terms of computationally efficient algorithm advancements over this period of roughly 3 years. And then, thirdly, things like software component libraries and compilers, other software development infrastructure and so forth is also improving, meaning the code that gets generated that ultimately creates the instructions that execute the computation for these deep neural networks is also getting more efficient by, again, roughly an order of magnitude. The beauty of this is that these three things compound. You get the improved algorithms running on the more efficient processors with more efficient code generated by better tools, and you get something like a 25,000x improvement, which I realize sounds insane, but if you do the math, this is actually what's happening over a very short period of time. Think about that, like what else improves by a 20,000x in a short period of time? I can't think of anything else, and this is really revolutionizing where computer vision can go based on cost, power, and size constraints. We have, last time I really did a careful count was maybe a year and a half ago, I counted roughly 50 companies developing processors for deep neural network training and/or inference, most of them focused on inference. It's a kind of Cambrian explosion. Many, many companies, large and small, silicon companies, silicon IP companies, are developing processors optimized for these workloads. I've listed on the left here just the, 20 or so who happen to be Embedded Vision Alliance members out of that field of roughly 50. And then in the lower right-hand sector of the slide here, I borrowed a figure from Ren Wu's presentation yesterday, Ren Wu of NovuMind, that gives some sample data showing how NovuMind's processor, which is tuned for these workloads, compares to other processors. The interesting thing here is most of these other processors that Ren compares with are already optimized for deep neural network workloads. So he's showing roughly an order of magnitude improvement in performance per watt over a previous generation of already optimized deep neural network processors. If you then go back and compare to earlier processors that were not optimized for these workloads, that's where you get the 200x kinds of numbers. So enormous improvements in processor efficiency, as well as algorithm efficiency, as well as generated code efficiency through tools. When we go to our survey and ask what kind of processors people are using, I was startled to see how many people, almost a third of the respondents, already using dedicated deep neural network processors. That's shocking to me because that's a category of processors that almost didn't exist 3 years ago. So for something to be adopted that fast is really amazing. By the way, if you're wondering why these numbers add up to more than 100%, it's because in many cases people use multiple kinds of processors in the same system, and we ask them to give us their top 3 most commonly used processor types in the survey. The fourth and final trend I want to discuss is what I call democratization. And what I mean by that is that it is getting much easier. Not to say that it's always easy, but it is getting much easier to solve certain kinds of computer vision problems without necessarily having to know an awful lot about computer vision. And that's huge because, as I said, there's a very limited supply of computer vision experts in the world. But not only is it getting easier to create the solutions, it's also getting easier to scale them, to deploy them at scale. And why is this happening? What's behind this? Well, it's a few things. One is, as I touched on a minute ago, deep neural network algorithms themselves help with this because instead of needing a team of 50 engineers handcrafting algorithms based on hundreds of man-years or thousands of man-years of accumulated expertise about handcrafting computer vision algorithms, instead we can, in many cases, select an algorithm from the literature, a deep neural network algorithm from the literature, and train it with our own data to solve our particular problem. Second, development tools of all kinds for algorithms, for optimized software, for computer vision and deep learning are improving very rapidly now because of this acceleration of innovation. In that early slide I showed the acceleration of innovation in startups, but of course, the acceleration of investment in startups. But of course, big companies are investing too. Companies like Intel and Google have thousands of engineers working on things like development tools to enable training and deploying deep neural networks. And then thirdly is cloud computing. Cloud computing, I think, is really a disruptor here and an accelerant in terms of making it easier for people to solve problems using computer vision. I hope some of you saw Chris Adzema's presentation where he implemented a face recognition system for law enforcement having zero background in computer vision. And it's something that's now been deployed and proven in the field. And that's the slide I have in the inset here. So why is the cloud such a big deal here? Well, if you compare cloud, implementing computer vision in the cloud versus implementing computer vision at the edge, there are a number of things that the cloud is just much better at. Time to market, for example. I mean, in the time it can take you to get a development board booted up and this SDK working for an embedded processor, often you can have your first version of your application already running in the cloud because you don't need to spend time getting things set up. The cloud providers have already set them up for you. Similarly, you have as much computing power as you need in the cloud. So if you decide you want to run more powerful algorithms that are more computationally demanding, that's fine. Use more powerful cloud instances or use more of them. Or if you just have the occasional need for more computation power in your application, again, that's fine. That can be accommodated in the cloud. You don't have to size your processor for the worst case use case as you do with an embedded device. So the cloud really gives many advantages, both in terms of ease of use for quickly building up an application, and secondly, for deploying an application, a vision solution at scale. Think of a company that's trying to build out some kind of video surveillance, or like we had Cocoon Cam here earlier today, building a baby monitoring application where they want to support millions of cameras out in the field. Well, it's one thing if you're Comcast or Verizon doing that, you have your whole infrastructure, massive nationwide, if not global infrastructure already. But if you're a startup, building up infrastructure to support 1 million video streams coming in, that's going to be prohibitive, both in terms of cost and expertise. But if you can just go to Amazon Web Services or Microsoft Azure, it's no problem, both in terms of the complexity of getting that working and the cost of getting it up and running. It's now much, much more accessible than it was just 2 or 3 years ago. And we do see, I showed this slide this morning, in our survey, roughly half of the respondents who are doing deep neural network inference in their applications are already using the cloud to do that inferencing, either exclusively the cloud or a combination of cloud plus edge, as indicated by the fact that those first 2 bars add up to more than 100%. I think I already pretty much covered that, so I'll move on and kind of summarize here and wrap up in a minute or two. So in conclusion, as I said at the outset, we are entering an era, I think it's very clear, of much faster, larger investment, innovation, and deployment of computer vision. I think we're going to see more deployment of computer vision in the next 5 years than we've seen in the last 50 years. That's fueled by these 4 factors. Computer vision is working. It's good enough, accurate enough in many applications, thanks to better algorithms, thanks to 3D imaging being more accessible, as well as other factors. Number 2, computer vision is increasingly cost-effective to be deployed. Number 3, computer vision is increasingly accessible to non-experts. So a combination of better algorithms, affordable 3D, and the cloud are really driving, I think, unprecedented acceleration in the use of computer vision and the deployment of computer vision to solve real-world problems. So where does this lead us? It leads us to products like Google Clips, an AI-based camera that takes pictures of things that are interesting, comes with an initial idea of what it thinks is interesting, and then over time can learn what you think is interesting. It leads to things like Dean Kamen's iBot 2 having spatial perception and safety features, and eventually autonomous navigation. And I get asked about self-driving cars a lot. A lot of people want to know, when are self-driving cars going to become mainstream? I have no idea. But to me, that's a secondary question. I'm much more interested in all of the other autonomous things that are already being deployed, like iRobots, vacuum cleaners, like Dean Kamen's wheelchair. And to me, cars are just one of hundreds of autonomous machines that are being deployed thanks to computer vision. And I'll leave you just with one of my favorite examples. Could I have the audio up on this one? So I don't know about you, but in my house, the self-parking shoes and furniture, I would totally pay for that.
That's great, Jeff.
Thank you very much.
Thanks, Jeff. It's a great presentation. Yeah, if we can just apply it to my kids' rooms, that'd be
Exactly.
awesome,
That's
the
exactly
entire
what I'm
thing.
talking about. Yep.
So if you have any questions for Jeff, we got a few minutes for questions. If you can make your way to one of the 2 microphones here, that'd be great. I have a question for you, though, because I'm constantly amazed at where DNNs are being applied.
Yeah.
And it's constantly surprising me. What's the biggest, you've seen more than I have, what's the biggest application space where you've seen DNNs applied?
That's
They wouldn't expect.
so I mainly focus on visual perception stuff, and I think to me, I don't know if it's the biggest, but to me, kind of the most amazing and most sort of both fascinating and promising and also a little scary is understanding human behavior, right? Human behavior is a mystery even to humans,
Sure.
right? And what you really want in something like an autonomous car or a surveillance system is not just that there's a person there, but what are they likely to do next?
Yeah.
Yeah, and it looks like we're pretty close to being able to have that.
Computer vision's applying the book Blink comes to mind, where the small little micro emotions that get picked up that
Right.
our subconscious might pick up, but you imagine computers picking that up. That'd be pretty fascinating.
Yep.
Questions?
Hi, Jeff. Thank you for the talk. I was looking at the shift from embedded to the cloud, and I keep thinking about this because of our application. There is no free lunch. The cloud costs, and it can cost a lot. How do you see that we can make a trade-off between computation in the edge and computation in the cloud, and whether there are things that will shift the trade-off?
Yeah, it's a fantastic question. Thank you, Mario. And I think the answer is, of course, like many things, it's one of these multidimensional optimization problems where the constants are not constant, right? Like if you saw the talk from Cocoon Cam this morning, he showed a trend of cloud computing costs over time, and they're coming down pretty fast, but in a nonlinear way. So somehow you have to kind of forecast that. I think, so if I had more time to elaborate on the cloud versus edge thing, a way I would sort of qualify it is to say often the fastest way to get a product out is to rely on the cloud. But over time, the most economical way to keep a product in the field is going to be a balance. And I see a number of companies making very clever trade-offs where certain things are done at the edge that make sense at the edge, certain things are done in the cloud that make sense in the cloud, and they kind of optimize across many of these factors, including the fact that the cloud costs, the network bandwidth costs, that you can't always rely on the network working, and so on.